My name is Fabiane Nardon, not Nardon, I'm not related to the Brazilian assassins. And, but I'm from Brazil, and I'm actually one of the founders of the Java user group from São Paulo. It's called SoJava. So Java is considered the largest Java user group in the world. We had some time ago around 10,000 members, so it's pretty big. And I feel that New York is like a sibling jerk from São Paulo, because São Paulo is pretty much like New York. If you have been there, you'd feel like home. So it's the financial center of Brazil. The largest companies are there. We have lots of traffic jams, just like New York. Subways, lots of people, lots of diversity. Almost nobody from São Paulo was born in São Paulo. Everybody comes from another place. I imagine that's like New York as well. And so Rodrigo is missing his city right now. Right? So it's
Bombay.
What?
Looks like Bombay.
Yeah, I could go to Bombay as well. So it's,
Yeah.
but so in São Paulo we have a huge Java community as well. And I've been working in data science for 7 years. Before that, I used to work with large data sets. But data science kind of started 7 years ago. I mean, there was data science before, but the buzzword became really relevant 7 years ago. So I think you've seen it all. I've seen tools raise and go down, and things changing, and roles that didn't exist now. So for example, when I started, we used to do everything. Like we would create the data and do the artificial intelligence and do the statistics and do everything. And then things got more specialized. So either you were a data engineer or a data science engineer or a DevOps data science engineer. There are several roles. And now they are talking a lot about the role of full stack data science. So I think that they're going back to where it started. Anyway, are there any data scientists or data engineers in the room? A couple, okay.
Starting.
Yeah, so if you ever tried to read data science tutorial or doing some Kaggle challenges, you probably came up with, usually you have a data set and you have a problem to solve, and then you use artificial intelligence or statistics to solve, right? And I think that when you learn data science in this way, you kind of live in what I call the data science fictional world. So in the data science fictional world, usually there's no big data nor legacy code, right? Because they give you the data set, and you have the data set, you usually run everything on your own machine, so you don't really have big data, right? And you don't have legacy code, so you're probably work a lot in the financial sector when over the years you create several libraries to validate your data and everything. But if you're doing this in the fictional data science world, this simply doesn't exist. You have a problem to solve and you create new algorithms from scratch. So the second thing that happens in the fictional world is that when you finish your experiments, your job is done. Like it's only the fun part. You get a data set that is ready, and then you run some machine learning algorithms, artificial intelligence. You feel really good, you solve the problem, then it's done. Right? You don't have to put in production, you don't have to control the log files or to monitor your jobs, none of that. And the third thing that happens in the fictional world, everybody always has a data lake with all the data you need ready to be used. Right? But of course, you can imagine that this is not the real world. So when you're doing data science, usually you have to run a pipeline that's something more or less like this. So usually you have several sources of data, and this is raw data that you're going to use in your system. So this can be either your transactional database that you're going to import in a, I don't know, in a data lake or something to do some computation. It can be log files. It can be data that you got from some open database somewhere. So it can be anything in several formats, several databases, files, and everything. So this is the raw data. And then you have to do lots of cleaning and transformation. So for example, if you get log files, usually you have lots of noise, and you have to transform and clean and validate. There's a lot going on to be able to use this data. Then you have a phase where you do feature engineering, which you apply several techniques to transform the data in features that are going to be used in your algorithm. So for example, you can transform dates in months of the year or in years, depending on the problem you want to solve. So this is feature engineering. And then usually you have data augmentation, because there are many problems in data science that you can't solve with only your data. So it's very common to get third-party data to augment your data set and then solve the problem. For example, you can buy data from a bureau somewhere, or you can download data from an open source data that is out there, and then, for example, with American Census or something, then cross with your data to augment your data and then solve the problem. And then you have the fun part here, it's the modeling, when you're going to do statistics or artificial intelligence machine learning to actually solve your problem. From this you have insights, and then you need to do some form of visualization to be able to show what you learned to the world. So it's either doing graphs, or you can have visualizations that are just tables or something like that. So your data science pipelines look like this, more or less. Yes? Okay. Cool, they are the same in New York and in São Paulo. Right. So the interesting part is that the fun part, what everybody does, is this part here. So if you say, I'm a data scientist, what I want to do is this part, it's just the artificial intelligence, the insights, and doing what, if they would do a movie about data scientists, the only part that would be in the movie is this part, right? But the rest of the problem, which is called data engineering, is really the hard part. In fact, 90% of the work in data science projects is spent in data engineering. So the part that's not glamorous. So this is a very interesting article, if you want to read, that shows how everybody tried to solve the artificial intelligence and statistics part of the problem, and didn't pay attention to the other 90%. And now we are in a situation, in a moment in data science, that we have lots of people that know how to solve the problem, but they don't have the data to solve it. And I know many companies that hired, I don't know, 10 data scientists, and they have work for maybe 2 or 3 of them. Because the rest of the world that's preparing the data and transforming the data is the real hard work to be done. And it's interesting that although 90% of the work is data engineering, if you go to GitHub, for example, and you look for machine learning projects over there, you have almost 200,000 projects, right? But if you look for data engineering, feature engineering, data lake, for example, and sum the number of the projects, you have less than 10% of the number of projects in machine learning. So really, in the last years, there was a lot of investment in machine learning and not enough investment in solving the other part of the problem, which is data engineering. And what's interesting for us that we are Java developers is that many of these problems can be solved by architecture, by software architecture, using Java especially. So, going back to this pipeline, it's not very hard to do one of these pipelines, right? If you want to do it once, probably your software developer minds are already thinking how to do this. You would be, I don't know, a main method, and then call all the parts and transform and everything. So this is not hard. What's hard, what make it hard is scale. So usually you don't have to do one of these pipelines. Usually you have to do hundreds or thousands of these pipelines. And then things become very complicated because how do you monitor it? How you run efficiently? So if you work for banks, you probably have unlimited amounts of money. It's not my case. Usually I have to do a very, very good software and use as less machines as possible to keep things under control. So just to give you an idea of volume, in my company, we process 3.5 billion new records per day. And we are running right now 4,600 pipelines per day. Okay? So it's a lot. It's a lot to control and monitor and create. So, going back to this. So of course there is big data, although right now there are several tools on the cloud, like Google BigQuery, for example, that you can just put your data over there and not worry if it's big data or not. But still you have to have some kind of distributed processing, either yourself or using one of these third-party tools over there. And you have legacy codes that you can use. So imagine that in your company you created, for example, methods to validate social security number, or to, I don't know, convert your bank, or validate your bank account number or credit card numbers. You probably have all these methods in place that you can use when you're going to validate your data, right? So you need a data lake that everybody's talking about, but you also need some kind of code lake. So imagine that you could use your Java code that you already have in your company in distributed processing and in your data science pipelines. So you can do this, and there is a tool that's very good for that. It's called Spark SQL. Do you know Spark? Yes?
Yeah.
Yeah, more or less. So Spark is Apache project, very popular in data science. What it does is basically process big data in a distributed way really fast, using lots of memory. So when you have a Spark cluster, usually you have several nodes, and you just submit a job to that node, and then Spark is going to take care of everything, split the data in different chunks and process everything, then put everything together again. So it's a really popular tool that basically everyone in data science knows and uses. And Spark is actually made in Java and Scala. Right? Spark is a lot more than this, just a distributed framework. It's actually an ecosystem with several other tools, including machine learning libraries. And there's one tool that is very interesting for us Java developers, and I'm going to tell you why. That's called Spark SQL. So Spark SQL is a language that you can use to interact with your Spark cluster and send commands to it, right? And this is Scala. So, for example, if you look at this code here, you have, I'm just reading a file, right? And this file is going to this variable here that in Spark is called a data frame. So data frame is like a pointer to this data. Then I can apply, for example, filters, like I'm filtering this data, and then I can just, for example, write the output to another file. Right? So it's very simple. So you know that the most used language in data science right now is Python, right? You know why? Why, if Java is the most used language, programming language in the world, why people in data science are using Python and not Java or Scala?
Libraries, Panda.
Libraries, pandas.
It's got REPL.
High speed.
REPL, yeah.
Jupyter notebooks.
So, Jupyter notebooks, exactly. So you got it. So let me show you something. So that's true. So in Python it's very easy to do experimentation, and because you can do interactive execution. But actually with Spark SQL and with Spark Shell, you can do the same thing in Scala. Right? So for example, this is a Spark Shell, and I can just copy and paste to make it faster. But I can, for example, do the same thing, like read a file, right? And then I can, for example, here I'm doing an aggregation. So this file has prices of apartments in São Paulo now, several neighborhoods over there. And then what I did was just an aggregation by neighborhood and showing the mean of by neighborhood, right? So you have more or less the same thing that you have in Python using Spark Shell. And you can also, you have like hundreds of functions, average, regular expressions, lots of, probably everything you need you have with Spark SQL and using Spark Shell. And you have a kind of Jupyter notebook, what is called Spark notebooks. So if you know Jupyter, it's exactly the same. So notebooks are very popular in data science right now, and a notebook is a web application where you can combine text, like a wiki that you can execute code, so you can combine text and code, and this code is actually run in the Spark cluster. So for example, here I had the same command I showed before, that I can execute here. I can, for example, show what is schema, because when you do two data frame, Spark is going to read the file and try to infer the schema of this file. So it inferred by the header, it got all the fields and inferred that everything was a string. And then you can say, for example, the same thing, aggregate the result by neighborhood, and then you can even plot graphs like this. So it's basically a Jupyter notebook that runs Scala in a connect to a Spark cluster. Right?
I think so. It's important to highlight the fact that we're talking over here that this data is scattered all across the various nodes.
Exactly. Yeah. So this data, when I was processing this data, it is not being processed on this machine. It was processed in a Spark cluster in a distributed way. So this file, this is a very small file because it's running on my machine, but it could be a terabytes file, and Spark would handle that. I actually have this Spark cluster here. So my Spark cluster has only 2 cores because it's running on my machine, but usually you can have hundreds of different cores, and when you run the notebook connect to a Spark cluster, you can process really large amounts of data. Right. Okay, so you can use, using Spark SQL and Spark notebooks, you can do pretty much lots of things that you can do with Python right now. With the advantage that you can reuse your Java code with Spark SQL as well. So, let me show what you do. So I was talking about creating a code base, right? So imagine that this is Spark SQL, and I decide to use my code with Spark SQL. So I can, for example, this is a Java class here. I created an instance of this Java class. It's a Scala code, but it's a Java class. And I registered this function here, and then I can use Spark SQL calling my function or my Java code, my legacy Java code from Spark SQL. And this is going to run in the cluster, right? So what we did to be able to use that is to create a plugins architecture that pretty much extends Spark SQL with three things: semantic data types, transformations, and aggregations. So why you need semantic data types? So in Spark SQL, when you are reading a file, like I showed you, it tries to infer the schema for you, right? So if you got this file, it inferred some of these fields are really strings, and some are not, like latitude and longitude are doubles, so it could be a different schema. So what you can do is just, you can create your schema, and then say to Spark SQL, just read the file, but using my schema. So I corrected, I said, this is double, this is double, this is double, and then when Spark SQL reads this code, reads the file, it's going to use my schema and then do it right. So this is important because if you read with the right schema, you get validation, right? So if there's a string in the file that is supposed to be a double, it's just going to ignore that line, right? So imagine that I have strings, I have doubles, but if I want to have my data types as well. So for example, I can create, like this is a Java class that creates a social security number Spark type. Right? So it's pretty easy, you just have to implement this interface here, and then you can call your code here, validations, whatever you want. So what's the magic of this? So imagine that now, instead of just having strings and doubles and integers, I have data with semantics. So I have data that's a social security number. So I can say to my schema that this field, SSN, is from this type. And then when I read the file, if this is not a social, if one of the lines does not have a social security number, the validation is going to automatically validate this field from me, right? And with this, you get several benefits that are in the long term is going to be a game changer for you. So first, one of the biggest problems in data science is when we are loading a new file or a new database is to create some kind of catalog, to know what data is actually in there. Sometimes you have the schema, sometimes you don't. And doing this with these semantic data types, it's very easy to create type detectors. So for example, if you have a field that you don't know what it is, but you can very easily examine this data and detect that it's a date, for example, or it's a social security number, or it's a person name. It's very easy to do this kind of algorithms. If you do that, you can have more intelligence in your data lake and detect the data automatically. This is something we are doing. Another thing you get is validation. So once you have your data types defined, when you load the file, you're going to validate everything automatically. You can have a better privacy, and I know you don't have GDPR in the United States, but if you interact with European companies, you probably have to be compliant with GDPR. In Brazil, we have something similar that's called LGPD, but it's almost the same law. And if you have semantic data types, you can also enforce privacy. So imagine that you have a social security number, right? So you know that this is PII information, personal identifiable information, so it should be anonymized or something. And if you have the semantics, you can apply the privacy correctly. And something that in the future can be possible is do automatic feature engineering, right? So right now the feature engineer is more like an art. You do by hand using your knowledge or the expert knowledge. But there are some tools already that try to do automatic feature engineering, like apply transformations to the data that makes sense. If you have the semantics of the data, this is going to be possible easily in the future. So if you have semantic data types, the other things you can do are simpler. So you can create your own transformations. You just have to implement one of these Spark SQL interface, like UDF3 if you have 3 parameters and so on. So if you notice here, I'm calling my code from a Java class inside and encapsulated this in a Spark SQL function. So when I run the code, Spark SQL code like this one, calling my function, I'm actually calling a Java code that I implemented. So it can be a legacy code, right? It can be Scala code, it can be several other languages that can compile to the JVM. Right, so with this, you can create your pipelines and actually using your code that you have in Java and in your company. Same way, you can do aggregations that are pretty easy. For example, this aggregation here, I'm trying to find what's the newest record from a list of records. So I just have to extend this class here. And there's some code to do that I'm not going to show here, but it's pretty easy. And then you can have aggregations as well, right? And then, same thing. For example, here I'm grouping the records by ID and trying to get the newest record from that set. Right. So with this, you can use your legacy code in a big data environment because you can encapsulate everything using Spark SQL. You can have the same benefits as Python to do interactive execution. You can have notebooks, and it's really powerful. So, what's the problem with experimentation and production? So there's a huge gap between both of them. Experimentation is the fun part, and what's really gets the job done is going to production, right? So what's the difference? When you're doing experimentation data science, usually you are using samples. Because if you have big data, you are not going to wait like 5 hours to process your data just to test a hypothesis or train an algorithm or something like that. So usually you need to have samples. And of course, creating samples is not as simple as it seems. Sometimes you can do just a random sample, sometimes you need something more sophisticated, but you need some kind of samples. When you go to the production, usually you're going to run your full data set with big data. Right now in data science, most of the experimentations are done with notebooks, and Jupyter is probably the most popular notebook out there. There's also Apache Zeppelin, that's used. This one I'm using is called Spark Notebook. It's basically the same thing as Jupyter, but running Scala and with a better integration to Spark. And it's a Java application as well. And in experimentation, we have interactive execution, so we are executing one piece of code, seeing the result, this is what I want or not, and then redoing the work. When you go to production, you are going to run in your big data, you need some kind of schedule, because usually you finish your pipeline, you did experimentation, and you're going to run this multiple times, for example, to structure data once a month or once a week, or when new data is available, whatever. Usually it's a batch execution, so we are going to run this in a, I don't know, a Spark cluster, and nobody's going to press play. It's going to be running batch. And then you need logs, because you need to know what happened, right? If it was successful or not, how much time it took, and so on. So getting a pipeline that you created in the experimentation phase and put in production is really not an easy task. So what we used to do when we were beginning, we would do our experiments in notebooks, right? So when we had the right formula to calculate, to generate graphics and everything, we just open IntelliJ, for example, and just code everything in a file that would be connect with some kind of scatter and generate logs and everything. Over time, this is not scalable, right? Because every notebook you do, you have to recode in a way that you can run in production. Over time, if you have 4,000 pipelines like we have, it's unbelievable hard. It takes too much time. So when I'm doing this experimentation with the notebook, usually if I have access to a data lake, especially if this data lake has samples that are already available, and if I have access to my code lake, which has all those full functions that I encapsulate in Spark SQL, I can do a notebook with code that could run in production, right? The difference is that if I'm going to run this in production, I need to have some kind of scheduler and some kind of parameters, so I can say, now run this over this other set of data or over this other month, for example. So if I can combine this, maybe I can run directly my notebook in production, right? Because the code is Scala code that is going to run in Spark SQL. So that's actually the solution we did. So now we create our pipelines in notebooks and then connect with our platform that's going to run these directly in production. So the same code that we're running during the experimentation phase is the same code that's going to run in production, right? So this is how it works. So we have a scheduler. We created our own, but there are other schedulers out there like Airflow, for example. That's an open source project that you can use as well. Then when it's time to execute a pipeline, the pipeline goes to some sort of pipeline GUI, and then you have to apply lock over your data lake, because especially if the data is stored not in a database, which is usually the case, like in a S3, Amazon S3, or file or something like that. So you have to acquire lock over it. And then you can execute the pipeline. And then when you start to execute the pipeline, you call your notebook. The notebook is actually a JSON file, right? So it's very easy to parse. And if you use Spark notebooks, the tool I showed you, it's a tool that's made in Java, and you actually have the parser of the JSON file in there. And the format of the JSON file for the Spark notebook is exactly the same format as the Jupyter notebook JSON files. right? So you could either get a Jupyter file if you wanted and apply the same parser and execute it. So when it's time to execute the pipeline, the notebook, we are going to get the file, parse the file, send the file to the Spark cluster, and then execute it. And I don't know if you noticed, but when you execute a notebook, right here, you see that in the notebook you have the comment and you have the result as well, right? So the result is here, and the result is here, and the graph here is the result. So if you save this notebook, it saves the comments and the result. So if I open this notebook again, I'm going to have it executed, right? So this is how notebooks work. It's the standard. The cool thing is that when you execute the notebook, the resulting file can be used as a log file, right? Because you have the comment, you have the output, and we even had how much time it took to execute any of these cells. So this is the perfect log system for your pipelines, right? So if you need to go back in time and see what happened, you just have to open your notebook and you can see the execution that was actually done in batch and not using the notebook tool. So this is the solution we implemented to solve the problem of using our legacy code and eliminating the gap between experimentation and production. So the third myth in the data science fictional world is that everybody has a data lake, right? And it's ready with all the samples and everything. So this is obviously not the case. So does any of you have a data lake, or you have this lake? None? Or you have to? Today I was at Strata and they said that MIT says that 80% of data science projects fail because they can't access the data they need. So it's nobody has a good data lake right now. So, but if I want to do a data lake, what's the problem with the data lake? Well, the problem is that I have to get data from several sources and some way transform it to put in the data lake in a way, in a format that I can actually use, right? So what I have to do is some kind of data ingestion that could be done by a pipeline as well, right? So if I write a data ingestion pipeline that's going to get those raw sources, transform it, and put in my data lake, then I have my data lake well done, right? So if you look at this, imagine that to write this ingestion pipeline, I use a notebook, right? Because I can just get the data, read the data, do some transformations that I have to do, and then save it in the data lake. I can do this in a notebook. I showed how easy it is, right? So if I do this, and I attach a scheduler to do this over time, every time there's a new data, I have exactly the same architecture that I use to run the data science pipelines. Right? So I can use the same system to create the data lake and then to consume the data lake. And since I'm doing this, it's very easy when I'm running the pipeline that's going to save the data in the data lake to other pipelines that are going to generate the samples that I need. So I have a data lake with the data and the samples already done. So that's basically the solution that we are using to create these pipelines. It's really fast, very productive, because we're using the language we already had, all the legacy code we had, just encapsulating in a way that I can run this over a Spark cluster in a very efficient way. And So, just to finish, we have to talk a little bit about privacy. Until a very few years ago, data science was like everybody would do everything, but there was no concern about privacy, and of course, over time, people realized that this was something that we should start to take care. And as data engineers, we have the obligation of coming up with a better solution for this, right? It's not just for lawyers, it's something that we have to worry about. So there's basically 3 things that it's important to try to solve here. First is how to deal with PII information. PII is personally identifiable information, so usually it can be your social security number, your name, your home address, your telephone, any information that can actually identify you. This is a PII information, it's a sensitive information. There is always, especially in GDPR, in the Brazilian law, there's some several legal bases that you can use to prove that you have authorization to use that data. I know that in the United States things are not as formalized yet, but there are several regulations. I imagine that in the financial sector you have regulations like this. So either you need to have the person consent to use this information, or you have, for example, you have, there are one of the possible legal bases in Brazil is to generate the credit score for this person. If you are using this data for this purpose, you are allowed to use the information. So you need to have some control of what's the legal base you have to use this data. And last, data lineage. Data lineage is a hot topic right now. It means that you need to have some kind of history of the data, because over time, if you get a data set, transform in another data set, and then transform in another data set, how do you know what was the legal basis or what was the origin of this third data set that was transformed over time? So when you have a huge data lake and lots of data sets, you need to have some kind of data lineage. So how this works? So for PII information, if you use that technique of creating semantic data types with a data type detector, you can detect that information. So the semantics of the data also have the information that this data is a PII data. So imagine that I have a phone number detector, and I detect that string that I received is a phone number, right? So I can say this is a PII information, and then you can automatically transform it in a hash, for example, to anonymize it. So that's what we are doing. So every time we detect that a particular data is a PII data, we automatically anonymize in the origin. So when the data go to the data lake, you have just a hash of it. So with this you can do your experimentations and still not expose the PII information. In the same way, if you detect that there was some PII information in the data, you can ask what is the legal base. There's a consent, or I had a legal obligation of getting this data. There's several possibilities. But it's very important to keep a record of what was the legal basis at the time. And for data lineage, if you use this same architecture, imagine that you have the customer database, then you run a pipeline on May 5th, and then this became another data set, the credit score. And then you ran another pipeline, and then it became the good payers data set. If you store all this history and which pipeline you run and what was the legal basis of each of these data sets, over time you can go back in histories and say, I can use this data set because these ones they're derived from customers, and they had authorization from the customers to use the data this way, right? So there are not many good data lineage tools right now. There are some that keep the history of the data and where it came from, but I don't know any of these tools that keep record of the legal basis that were used. So that's why we created our own data lineage tool, but that's something that needs to be solved as well. So, last message is data science is also about data, not just science. So, as data engineers, we have lots of problems to solve, and if you don't solve it, data science is not going to be as successful as everybody expects, right? So, this is my contact. If you ever go to Brazil, please reach out. I'll be happy to pay a Brazilian coffee. Very good coffee, right, Rodrigo?
Oh, yeah.
Yeah. So, thanks a lot for having me here. I hope it was useful. If you have any questions.
Thank you, Fabiane. Any questions?
So this notebooks that you store, you'll be storing in some source code management, like say GitHub, Bitbucket, something, and Jupyter notebooks would be like JSON file. So how do you really diff between those?
No, you're not, because that's one of the problems with Jupyter notebooks. When you change it, and if you store on Git, for example, since it saves the execution as well, every time you execute, it's a different file, so you don't want to actually keep track of the changes. So what we do is that we don't save the notebooks with the execution, so we parse it, and we save the file without the execution, but it's in our own system, in our own database. We don't use Git for it.
But even if you save it without the execution itself, it's a JSON file, which is huge, and still it is not like comparable.
Exactly.
So
yeah, so that's why we parse it, and we actually save the parsed object in MongoDB. That's how we do it. And then when we are going to execute it, we parse it, we serialize back to the JSON file.
Just a quick question. You showed the pipeline and you showed where Spark was interacting and you had the data lake.
Yes.
Now the data lake is probably not going to remain constant. You have changes to the data structures that you're putting in there. So the question of metadata comes up. How do you keep your metadata fresh? And how do you make sure your pipeline is using the right metadata?
In our case, we have wrappers over the read method. So instead of just calling that method that you saw, we call our read method that's actually reading a catalog that we have and checking the schema and see if the schema is the schema that the pipeline needs. And if the pipeline breaks because we changed the data or the schema or something, we deactivate that pipeline and send an alert to the one that created saying your pipeline is not valid anymore because the data changed. So we decided to do this way instead of just prohibiting the pipeline or the data to be changed, because we know that the data is going to be changed over the time, so we prefer to just break the pipeline and deactivate it and then send an alert. That's...
Well, you combine that issue that you brought up. I mean, it's just one use case of privacy. Just because you have a program that can go to the data lake, maybe it shouldn't be accessing every bit of the data structure that it can. So you have the metadata that's actually telling the program what can you actually read from it.
No,
so some people are going to describe the metadata and say, this is the metadata, but only certain people can read it, and maybe some other program should just be able to see it as a wider field and not be able to drill down? How do you impose that control?
So the data lake has actually access control over it. So you're not. It's not that you have access to the whole data lake or nothing. You have access to a particular data set, and these data sets are actually controlled by us. So you don't have access to the real file, right? So you use one of our methods to read it, and you say, I'm going to read this data set here, and you have the idea of that data set. And then there's our software that goes to the data lake and read the schema, read the metadata and everything, and then get the actual file that for you, it's, you don't know how this is stored, but the software knows. So you don't have access to the actual raw file. Right? So we use the data frame abstraction to be able to read the data.
Do you have to build all this, or are you using any tools that are
We created everything ourselves.
Actually, I think we just hit the limit. So,
Okay.
So if you have a question, you can come up front. So thank you very much again, Fabiane.